Today, I continue the discussion of renormalization of phi4. Sorry, that's something that shouldn't have happened. No. I continue the discussion by introducing the notion of effective and running coupling constant and of renormalization group. So you have already seen the concept of renormalization group from the point of view of statistical mechanics, but I'm going to present a similar concept, which was in fact appeared before in the history of physics, but is connected to the concept in statistical mechanics in quantum field theory. So I'm going to discuss effective coupling constants or parameters, in fact. And renormalization group in quantum field theory. So again, I'll do that in the very specific framework of the massless phi4 theory in D equals 4 and in the Euclidean setting. So the theory is defined in Euclidean space-time, but this can be first the conclusion of this applied to Minkowski space-time as well. And we are going to discuss briefly the case of massive phi4 and maybe the case of what's happening in dimension different from 4. But I'll focus on this. So remember what we did last time, yesterday. Yesterday, I showed that it's possible in perturbation theory at one loop to define, starting from a path integral or a functional integral formalism, to construct the correlation function, in fact, the irreducible function, but from that you get the correlation function of the two-point correlation and the four-point correlation, which are ultraviolet finite. So they have no short distance singularity, so we can take the large cutoff limit and get a consistent theory in continuum spacetime, Euclidean spacetime, but continuum spacetime. And this was done by considering that one starts from a path integral with a classical action, but with it's called Baire parameter. So one starts from a path integral of the form integral d over phi of exponential of minus s r of i's, and the subscript r means renormalized because this will be defined in terms of renormalized quantity. It's not a classical action. So SR is for phi4. You can take an action that looks like the classical action of phi4. But the parameters here are going to be fine-tuned so that we get a finite renormalized theory. So they are not, from the beginning of the calculation, they have to be calculated. And what I did is that if I assume that the two-point function is, so the massless, that the fact that the physical mass is 0 means that the renormalized irreducible two-point function is a function of the momentum p as equals 0 when p squared equals 0. Because it means that the two-point function has a pole or a singularity at p equals 0. This means that the first physical state has mass 0. So this implies massless. Okay? And we have seen that this is going to fix the value of B. Because if you change B, you change the mass of the theory. So this requirement fixes B if A and C are known. Okay? So this fixes B. Okay? And we have seen that we can, well, if we want to express the observable of the theory defined by this path integral in terms of the value of the 4-point function at the specific reference point. So if we define a reference point in momentum space, which is defined by first a renormalization scale which is called mu, which is the reference energy scale at which I'm studying the process and defining what I'm computing. And, well, in our case, we choose P1, P2, P3, and P4, such that the reference, well, let me denote this by 0, simply by, so this is the reference point, which asserts that P1 plus P2 0 squared equal P1 plus P3 0 squared equal P1 plus P4 0 squared equal mu squared. So this is a choice. Okay, but some other can be chosen. Okay. This choice means that basically when you compute the 4-point function, the normalization of the 4-point function in the S channel, in the T channel, and in the U channel are the same. So it's symmetry under the change of channel. Okay? It's a convenient choice. And with this convenient choice, what we do is that we consider what is the value of the irreducible. So we compute with such a theory the value of the irreducible 4-point function at this reference frame, so P naught of 1 up to P1 of P0 of 4. And this is what we, by definition, call the renormalized coupling. Okay, this is a renormalized coupling. Okay, and therefore, since the irreducible 4-point function is defined out of this parameter, this means that we re-express C in terms of GR with change variable, because that's physical, something which is related to calculation or experiments, scattering experiment at the scale mu. Okay, and with this recipe. And so we choose this fixes B. This is going to fixes C as a function of GR. And, well, at one loop order, we don't need to change A. This is going to be needed at higher order. So what we did is that if we express everything in terms of G normalized, we add A equal 1. We had B equal, let me just remember, not to make any mistake. But I think I remember almost by heart. Yeah, here it is. B equal minus G renormalized 1/2 1 over 4 pi squared times lambda squared, where lambda is the ultraviolet cutoff. And C, in order to have this relation, is GR plus GR squared, and there was a factor of 3/2, 1 over 4 pi squared, and the log of lambda squared divided by mu squared. Okay? And that's a relation at one loop order, at one loop between the bare parameter and the renormalized coupling and the cutoff. And if we make this choice for the bare action, compute the irreducible function, express them in terms of GR, what we get is some ultraviolet finite endpoints irreducible function. Always at one loop. So what we got is that, for instance, that the irreducible two-point function as a function of p, the momentum. So this is just a two-point function. So we have the momentum, p, and we have the two-point function. This is going to be just p squared. And for a reason peculiar to the phi-4 theory, there is no correction to, if you want, there was a GR correction, but this correction is just 0. 0. And then we have two loops corrections that I have not computed, which require some additional normalization. Neglect. So this is two loops. Okay. So, well, let me just erase it. Okay. And for the 4-point function, irreducible function, which is a function of P1, P3, because we have that. We have our truncated legs here. We have momentum P1, P2, P3, P4, but P1 plus P2 plus P3 plus P4 vanishes, so P4 is fixed. This is going to be GR, that's a classical result, that's the tree level. And then we have minus GR squared, that's the result of the calculation, 1/2, 1/4 pi squared. And then we have log of mu squared divided by P1 plus P2 squared plus log of mu squared divided by P1 plus P3 squared plus log of mu squared divided by P1 plus P4 squared, which is P2 minus P3 squared. Okay? And then plus terms of order GR cube, which are the two-loop diagrams. Okay. And here I discussed just the two-point function, the 4-point function, but you can check that if you want to compute the at one loop if you want to compute similar to that the 6-point function, for instance, okay, we have seen that the irreducible 6-point function, the first diagram which appears is this triangle diagram, which is of order GR cube, but with 3 vertices. And first, since there is nothing before, we start from a theory which is a phi-4 theory. So a phi-6 vertex function can come only from the quantum interaction. It appears only at one loop. There is no tree-level contribution, no classical contribution to this. So this is the first diagram appears at one loop, which might be dangerous, but this diagram is ultraviolet finite already. In any case. So there is no need to introduce some, to adjust some coefficient in the action to makes it finite, because it's already ultraviolet finite just in the naive calculation. It doesn't require any renormalization needed. Okay, at one loop. Okay, so that's for the 6-point function. And the same for any 2m point function. It's m larger than 3. Which means that by this prescription, this choice of A, B, C, all the irreducible functions of the phi-4 theory are ultraviolet finite at one loop. And from this, we can reconstruct from the irreducible function the connected function, because from the irreducible function, we can reconstruct the connected function, because the connected function are things like that. They're made out of trees of irreducible function, and the short distance divergence can only be contained in the irreducible part. And then we go to the general function. Yes?
Yeah, so I'm confused. You say that up to one loop, there's no normalization needed there.
Yes.
Is that a statement that you argued, or you
no?
Just
I showed you.
Do the calculation.
You do the calculation here.
Yeah. So
this diagram, I think I wrote it 2 days ago. This diagram doesn't contain any ultraviolet divergence. If you want, I can repeat it. But the argument is that these diagrams, you see. So here you have 3 incoming momenta, P1, P2, and P3, which is minus P1 plus P2. Well, they may come for the 2 legs that are connected to this one, but the sum of the momenta, let me call it P1. So this diagram in momentum space, and then you have a momentum K inside that. So the Feynman rules is that you have to integrate over K divided by K, divided by 2 pi squared by 4. That's not important. And then you have 1 over K squared, 1 over K plus P1 squared, because here there is K, here there is K plus P1, and here there is K plus P1 plus P2, times 1 over K plus P1 plus P2 squared, you see. And you see that when K goes to infinity, this integral is convergent. Okay. It's just a rule of what's called power counting. I'm going to discuss that a bit later. Okay. And the same for the 8-point diagram. So the first diagram is this one, which is even better, because you have 1 over K squared, an additional 1 over K squared. So the larger the number of loops, the better the convergence. Okay. So from this you get to connected, and from this you get to the correlation functions. So at one loop, we are happy. All the correlation functions are ultraviolet finite. Good. So that's what we did yesterday. It took me a bit of time, but that's important. Have a good go after. Okay. And what I want to discuss today is first what's the relation between mu versus G renormalized? Because the choice of mu is arbitrary. That's the choice we did to define GR. And so, if you look at the expression, for instance, for the 4-point function, which is the only one we need, you can realize that if you choose a mu and a GR, then you get this result for the irreducible 4-point function. You get gamma 4 irreducible of P1. Okay. But you may have chosen a different mu prime, different from mu. So of course, if you choose a mu prime which is different from mu, but consider the theory with GR with the same value than the first one, you get a different value. But in fact, you can adjust GR prime so that you get the same 4-point function. You see? And of course, that's because GR is defined by the value of the irreducible 4-point function at a given reference frame. So if you go from mu to mu prime, what is the value of GR prime that you must take is just the value of this for the different P, reference P, so that P1 plus P2 squared is equal to mu prime squared. So from this calculation, it is obvious that GR prime is just GR, and then there is a minus GR squared, 3/2 1 over 4 pi squared, and then there is a 3/2 because there are 3 contributions times log of mu squared divided by mu prime squared. Okay, so this is a relation. Plus higher order terms, but I'm considering this as one loop. So this means that, you see, if I write here a plane where here I have GR and here I have basically log of mu, you see, if I consider a theory whose value of the 4-point function is GR when it is calculated at the scale or measured at the scale mu, here, I'm sorry, this is GR. This is, I have a first point, and here I have mu. Let me write GR here, and that's the value of the 4-point function. We normalize coupling. You see? If for the same 4-point function, for the same theory, the same quantum theory, I defined GR with reference to a different scale mu prime, and I get the GR prime, and you see that through this relation, this is a linear relation in log. It's something like that. So you have some relation like that. Okay. For all the points along this curve, all the correlation functions are the same. So the different points along this line describe the same quantum theory. The same quantum theory. Okay. While, of course, if you consider a theory where the renormalized coupling defined at the scale mu is different, it's a different quantum field theory. Because the coupling is Well, if you have this curve, it means that the coupling is stronger, is smaller at the same scale. You want to compare. Well, you can do that. No, I'm sorry. Sorry. If you consider a theory that at given scale has a different coupling G prime, it's a theory which has a smaller coupling. The interactions are weaker. So this line is a different. Yes?
And all those lines,
yes,
we will be, even though they are different
yes,
theories, they are all massless. They will be.
Yes, they are all massless. So this is the same theory. This is a different UFT, and they are all massless because that's a good remark. Okay. Good. And so, let me continue the discussion. So you see that in fact there is only a couple of mu and GR defines the quantum theory. But you change mu, you can change GR accordingly, so that you can compare your calculation done with different choice of mu and check whether you are computing something for the same quantum theory, the same physical system, if you want, or a different physical system. Okay? Good. So, this is going to lead to an important concept, and let me discuss it just now. So I'm not going to follow exactly the line of what's done in the lecture notes, but I think it's a good point to do this in this case. Okay, so you see that I have this expression, which is an important one. Okay, and so you see that you may consider that GR prime is a function of mu prime. Yes?
Yeah, so I'm a little confused. When we defined mu squared and
yes.
and GR,
yes.
Didn't we define GR as a function of mu squared?
Yes. No. We compute. No. We choose a mu r. We choose a GR. And then we compute the 4-point function for this value of GR. And we get the 4-point function for us in my calculation.
Isn't GR just, I mean, even if you look at that expression there, we can calculate the 4-point function given that B1 plus B2 squared is mu squared, right?
But you need to choose a value of GR. Either you take GR as a number extracted from some measurement, some experiment, or you choose it. You see? Or are you simply assuming that you already know the 4-point function?
There's still
what do you start from in your? Sorry?
There's still an ambiguity between A, B, and C.
No. There is no ambiguity.
Okay.
If you know the 4-point function, imagine that you have a theory, you know its 4-point function, and it has this form, it has this logarithmic dependence in p's. So imagine that you have making some, some Gedanken experiment, and you have measured for various value of the momenta, 4-point function, and you extract, and you have a curve, which is a 4-point function as a function of the momenta. So now You can choose the reference point. So you can choose the mu. You take the p's that are over the mu. You take the results of your experiments, and you get a number which you call GR. And you say, OK, my theory has this coupling, GR, at this reference scale mu. And now, once you have that, you can check that your theory is indeed a phi-4 theory. And therefore, now if you ask which coefficient in the action in a functional integral do I need to construct mathematically this quantum field theory, here are the value of the coefficient A, B, and C, given the choice of cutoff in your path integral. So there is no ambiguity. But you have just to be clear about what is the input of your calculation and what is the output. And if the input is well defined, then the output is well defined. There is no ambiguity. But you have to be clear about, one should be careful not to change what one considers the input and the output during the calculation. OK, so you see that if mu and GR are fixed, this relation defines that GR prime is a function of mu prime. It's just a parameterization of this curve when you express G as a function of log mu. Okay. And so I'm going to consider that GR prime is some function. Let's call it capital G of mu, given this being somehow the initial condition. Okay? And, well, this is a calculation, but it's a calculation at first order in GR, but so you may ask, perhaps the term of GR squared becomes important, because in general, this term is of order, is just of order 1. So it's better, in fact, to write this relation in infinitesimal form. So it's better to consider what's going on. Better write the relation in differential form. So extract from this formula how does GL prime depends on the variation of mu. So I'm going to consider how does GR prime depends on the variation of mu. GR and mu being fixed. So this means that simply I'm considering what is the logarithmic derivative of the function G. So this is, if you want, mu d mu of this big function G depend on mu. Of course, it depends on mu. Okay. And for this calculation, you just have to compute this. You just have to write that mu prime is mu plus delta mu. Okay. And so you get a factor here minus 2 delta mu divided by mu. So what you get is that this is GR squared 3/2 1 over 4 pi squared. Okay? So this is a differential form of this relation. Okay? So by definition, this is called the beta function relative to the coupling GR. So here I'm making, here I am making a variation when mu prime is mu plus delta mu. So I'm making a derivative, and then at the end, I fix mu prime equal mu. I'm just making an infinitesimal variation. So by definition, this is called the beta function. So take it as a definition. And the concept of a beta function was introduced by, I think, Gell-Mann and Lau in QED. But in the general quantum field theory, this was introduced by Callan and Szymanczyk a bit later. This was in the 60s, I think, and this was in the 70s, end of the 60s, beginning of the 70s. So it's called the beta function simply because it's denoted beta everywhere. So there is nothing, it's just the name of a letter. Okay. So this is the definition of the beta function. Okay. So this is the beta function. So this is the definition of the beta function. And this is the value for phi 4. So if you know the beta function, you know how you can, how the coupling G are vary with the choice of mu. Because you just have to integrate the beta function. To know how does dr depends on mu for a given quantum field theory, namely specific choice of mu 0 G reference 0, if you want to start from a point. You just have to integrate this integrate the, it's called the flow equation, mu dd mu of gr of mu equal beta of gr of mu. Because this is a differential form, but once you have it for a differential form, you can integrate it. If you write this curve in the opposite, here I write log of mu, and here this is gr of mu, so I just rotated my curve. What you see is that you start from some reference mu 0 and some reference gr 0, and if you want to know what is the equivalent gr of mu as a function of mu that describes the same QFT in QFT, then you just have to integrate this flow equation. Okay? Is it clear? So this is a flow equation, what is called the flow equation. Okay. Good. Yes?
I have a question. So we started with an action with those parameters A, B, and C, right?
Yes.
And we saw that we had to change in some sort of way
Yes.
our definition of them because
Yes.
we have the
Yeah.
UP divergence.
Yes.
Now, if along that line we have the same correlation functions,
Yes.
and we see that we move along that line and they are finite,
Yes.
is our starting point also in that line? Like, in the sense that if that thing was divergent, how did I escape to a line where everything is finite?
I'm not sure I understand your question, or perhaps there are two questions in your question. So
Maybe,
one,
yeah.
your question is, do you change A, B, and C when you move along this line? Is this the question?
Oh, I guess that we do, right? Because we go to another GR prime.
No. Because you go to another, when you move along this curve, or the curve here, the physics doesn't change. The 4-point function do not change.
All right. Okay.
And which means that it comes from the same functional integral. It comes from the same original Baire action. So A, B, and C do not change.
Okay.
And you can check that. Just take this relation, implement it into C, and you can check that C doesn't change. So in this relation, C prime is C. And if you had changed C, you would have changed the irreducible 4-point function.
Okay.
Yeah.
And so then the other question is, so where did we start? We started somewhere that our
Yes.
point functions have divergences.
Yes.
Is that any point in that plane or not?
The fact that there are divergences?
Yes.
Well, the fact that a divergence, in fact, you can view it as the fact that there is a log in this relation. Because there is a log, because in the calculations there was a log of lambda squared, which has to be cancelled by log of mu squared. So, but you can do the opposite relation. You see. You start from a renormalized theory with a finite renormalized coupling constant for a finite value of mu. And now you ask what's the corresponding coupling for a coupling of the order of lambda,
Okay.
the original cutoff.
Yeah.
Just by integrating this equation. You see? And when you integrate this equation, this is a derivative with respect of log of mu. So you are going to discover that the GR of lambda, you just take this expression, and you see that GR of lambda is GR minus GR squared, 3/2, 1/4 pi squared, log of mu squared divided by lambda squared. I just took this relation or integrated this equation up to the scale lambda.
Okay.
You get a log lambda, and moreover, inverse this. This is just C. See? Okay?
All right.
Well. So everything is consistent and closed system.
So I can go back to the divergence.
You can go back to
Okay.
the original. So GR of lambda in this calculation is just the original C. Good point. Okay. So, yes, where are my notes? Okay. So now, again, let me introduce the concept which is already contained here. The concept of, so this was the third blackboard. So I have introduced the concept of a beta function, a Calan-Simancy beta function. So now, let me see that the consequence of this calculation, or rather something that is contained in the calculation with it, is a concept of running coupling constant. And this is going to make some relation with Wilsonian normalization group. Okay? So let me now just So the calculation, okay, I didn't present it like this way, but we can do the calculation here. Let me just let me just start from the 4-point function that I wrote here, my irreducible 4-point function. So now it's a function of the momenta pi's. Let me just write the momenta like collection of momenta p1, p2, p3, p4. And it's a function of gr and of my choice of mu. Okay? And now, and I want to consider what's going on. I want to compare. I want to make a scale transformation on the momenta. So I want to compare a choice of momenta pi and the choice of momenta pi prime equal 1 over s pi. Okay. And so if s is smaller than 1, I go to high momentum. So if s much smaller than 1, this means high momentum. And if s is less than 1, this is low momenta. Okay? And usually in energy physics, one is interested in the behavior at high momenta. So one considers rescaling with respect to this factor 1 over s. But I'm taking s simply to make the connection with Wilsonian normalization. So I want to compare this irreducible function and with this irreducible 4-point function for the momenta pi divided by s, gr, and mu. Okay. So now, of course, they are different. They are different because there is a log in the explicit expression which was there. It depends on p. Okay. But now, if I divide p by s, instead of having the s as the denominator, at the denominator of a denominator, you can put it at the numerator. So you can put s, it appears like mu s. So you can see that this is equal to the irreducible 4-point function of the momenta. Gr is not changed, but now this is mu times s. Okay? And this is exact, in fact. It's going to be true to all orders, well, up to some normalization. This is exact because it comes from dimensional analysis. Okay. Gamma is dimensionless. It depends on some momenta, on some coupling constant, and on mu. Gr is dimensionless, so gamma 4, and gr are dimensionless. So it can depend only on the ratio of pi's divided by mu, which is a dimensionless quantity. So rescaling the pi by a factor 1 over s is the same thing that rescaling mu by s. Now we can use the renormalization group beta function to say that changing mu can be reabsorbed into a changing of gr. So the renormalization group beta function tells you that this can be re-expressed of the irreducible function, two-point function for this momenta. For the original mu reference scale, but a new coupling GR of S. Okay? So this is a trivial part which comes just from dimension analysis. This, going from there to there, requires relying on our renormalization calculation and the form of the renormalization. Okay. And you can check that. How does GR of S depends on S? Well, you can just do the calculation, and you can write a similar equation to this equation for GR of mu, which is S d over ds of GR of S is some function of GR of S. And it turns out that it's just a beta function. It's minus the beta function. Okay. So the important point is that there is a minus sign here. And there is a minus sign here because going to large S means going to low momenta, while in this definition for the beta function, one goes to going to large mu means going to high momenta. So that's why there is a minus. Okay?
You have like the same equation twice, but the dummy variable changed and suddenly
no.
This
S, S is not the same.
In that equation, S is just a dummy.
No, S is not dummy. S is I change S. You see. So what I'm stating is that if I increase S, okay, I increase mu. So going back to the original mu means that I have to go downward instead of going upwards.
You have a different function, GR.
I get a function which is minus. But the fact that there is a minus means simply that to go from there to there means I must to go downwards in mu. You see? It means that in order to go from there to there, I have to go from mu to mu prime, which is mu divided by S. So that mu prime S is mu. So that's why there is a minus sign. Okay? So do the calculation. It's an easy calculation, and you'll get convinced. Yes?
So those equations are telling us that if inside one renormalized, we consider one renormalized theory, and we probe different momentum scales.
Yes.
It's the same as staying in the same momentum and go to a theory with a different strength in the interaction.
Yes, it can be recast into that.
Okay.
Yeah. So you see, so this GS defined in this way. So I'm asking, yes, I rescale the momenta, and I'm asking, is there a difference coupling here where this can be compared to this one for the original space momenta? So you see, this GR of S is just this GR of S correspond to the running coupling constant with and here S is the inverse of a momenta. So with let's say length scale factor S, which is the inverse. So S is the inverse of momentum or energy scale factor. Okay? So because it tells you that at a scale P divided by S, the effective coupling is GR of S. And this is take this equals it, take this as a definition of the effective coupling constant, of a running coupling constant. And renormalization calculation tells you that in this quantum field theory, the coupling constant must be running with the scale. Okay. And in terms of a rescaling factor in position space, this is the equation it obeys. And if you make a rescaling in the momenta, so instead of that you rescale the momenta p into some well, I cannot. It's often called lambda, but they have already a lambda. So let me call it I don't know u high. And I'm interested in what's going on when u is growing. I have an effective coupling constant g of u. It's going to obey the opposite equation because rescaling the constant. So we are going to have u d of du of g r equal beta plus beta of r with a plus sign. Because yeah, I'm working in momentum rescaling. Okay? Good. So that's a property that comes out of the QFT, that comes out from the calculation we did. We construct the quantum theory, and we see that it has this property. And I hope you see some strong analogy with the kind of things you did in the statistical mechanics course when considering how the parameter of a statistical model, like the Ising model, parameters like the temperature, the magnetic field, scale when you perform a renormalization group transformation in Wilson cell. Very similar. In fact, the same. At that stage, it's very similar. Okay. So now, let me, I have a half now. So, what did I cover from what I wanted to do? Oh, I've not printed what I wanted to do, but that's okay. Okay. So now, what does this, well, what is the meaning of this beta function? So this beta function allows, once you have computed it, it allows to study and to compute how the running coupling constant scale with the energy scale or the length scale, which you probe your theory. Yeah. But you see, and so you see that it depends on the scale. So this is the consequence or the reflection of a very important of quantum field theory in this case, which is called the scale anomaly. So this calculation is, in fact, an example of a quantum anomaly. And I don't know if you have already heard about anomalies in the lecture course. An anomaly is if you have a symmetry of a classical theory which is broken in the quantum theory, so that cannot be satisfied in by any quantization scheme, this symmetry is said to be anomalous. There is an anomaly due to quantum effects. And let me go back to the classical phi-4. Classical phi-4, it is given by a classical action, massless, which is integral d4x 1/2 d mu phi squared plus g divided by factorial 4 pi to the 4. Okay, so I'm classical massless in d equals 4. Okay. This theory has an important property, which is that if I make a scale transformation by going from a classical field configuration, any field configuration, phi of x, and I rescale this by a factor s by considering that phi s of x is phi of x divided by s times s. Okay? So this is a scale transformation. So imagine that you have a configuration in X space of your classical field phi. Okay. What I am doing is that there is an S minus 1. Sorry. S minus 1. Yes. And I'm looking at that, I'm enlarging it. You see, I'm enlarging it by a factor S, but at the same time, I squash it. This is scale transformation. And I'm doing this because I'm calling that the scaling dimension of the field phi is -1. So when I make a scale transformation by a factor s in momentum space, I rescale by a factor s minus 1 the field. Okay? Good. So under this scale transformation, you can check easily that if you make a change of variable, that the classical action, oh, I'm sorry, this is a very bad denomination because this is the action. So let me write this A. This is the action. A. Okay. That A of phi s is always equal to A of phi, original phi. So the action doesn't change for any field configuration. Okay. So this means that the phi-4 theory, the massless phi-4 in 4 dimensions, has a symmetry which is scale invariance. Okay. In fact, it has an even bigger symmetry, which is conformal invariance. Which means that we can extend this to the non-local transformation. But, okay. And that's particular to 4 dimensions. It's not scale invariant. So it means that when you make a scale transformation in the classical theory, G doesn't change. Okay. Now, the fact that in the quantum theory, G of S depends on S, the G renormalized depends on S, on the scale transformation, means that this symmetry is broken. This symmetry is broken. Okay. You can, for instance, state that if you replace the classical action by the quantum effective action, and this classical field by a background field, this is not equal to this. So you can say that, for instance, the quantum effective action of a given phi s is different from gamma of pi, where this is a quantum effective action. Okay. another way to state this trace anomaly. So this is called the scale anomaly. Scale anomaly. Is that classically, if you have a quantum theory, if you have a classical symmetry, Noether theorem tells you that you have a conserved current. Scale symmetry implies conserved current. G mu scale with G mu G mu equals 0. Okay. So you can compute the conserved current, and that's a calculation. Well, I can do that, but basically let me just explain that. Well, I can write it, but so this G mu scale, if you do the calculation, it's just a classical application of the Noether theorem. You find that this is T mu nu x nu, where T mu nu is a stress energy tensor. That's the conserved current of translation of the theory, plus phi d mu phi. Okay. That's a classical theory. Okay, and T mu nu contains phi 4. So T mu nu is d mu phi minus delta mu times the Lagrangian, 1/2 of d phi squared plus g divided by factorial 4 phi to the 4. Okay, so these are just classical results. And now, in the quantum theory, when you take this classical current and compute its divergence, you do the calculation, and you find that there is a quantum correction that comes from the one-loop diagram, and that comes from the fact that there are ultraviolet divergence. And if you do the calculation, what you found that this is an operator. Because in the quantum theory, G mu is a combination of fields with a quantum operator. And you can check, you can do some symmetry analysis and check that d mu of G mu has the quantum number, namely the dimension of the operator phi 4. So it may mix with phi 4. And if you do the calculation, you find that this is precisely the beta function of G renormalized. Okay. So the beta function of the renormalized appears as the coefficient of the anomaly. Okay? So if you have never heard about anomaly, I think in a course in advanced quantum physics or in high energy physics, you are going to meet a very important anomaly, which is called the axial anomaly, which is an anomaly of quantum electrodynamics. When you have massless fermions, you have a symmetry, which is also anomalous, and this anomaly has very important consequences for physics of mesons and low energy states of hadronic physics. Okay, this is the first example of an anomaly. And anomalies are everywhere in quantum theory, in high energy physics, in string theory. Well, it's a very important concept. Okay. So I still have whatever now. So let me just discuss two things. First, Well, I could discuss the renormalization of the massive theory, but that's a bit, well, that's a bit technical. So perhaps I will skip that. You can find it in the note. You can renormalize in the same way the massive theory. Of course, the massive theory is not scale invariant, but still. So there is an additional renormalization. Massive theory. And well, perhaps what I can do is just give you the result and leave it as an exercise. I think it may be an exercise of a tutorial. I don't remember. There is a tutorial? Yes. OK, so massive theory, I leave it to a tutorial. It can be normalized. But this requires the definition of a renormalized mass. MR. Because now we have a theory with two parameters, the Coupling constant and the mass. So you have to define what is a renormalized mass and check that if you define the renormalized mass in a way that the theory is finite in terms of the renormalized mass, then you can introduce count term, but you have to change B. So B has to be adjusted. So the formula we have for the massless theory for the counter term B requires an additional normalization. Okay. So massive theory. Okay. So I can have two points of view. So first, so let me go back to the calculations that we did here already. Let's go back to the running coupling constants. Okay. So we have seen that, and this transformation. So we have seen that if we perform if we compare the coupling constant at different scales, they are obtained by integrating this equation. So we may compare under a scale transformation, or under a change of variables. So if I start from a scale mu naught with a coupling, renormalized coupling GR naught, and I'm asking at scale mu, what is the equivalent coupling GR of mu? I just have to integrate this equation, mu dd mu of GR of mu equal beta of GR of mu, which for the 5-4 theory is this coefficient, 3/2 1 over 4 pi squared GR squared of mu. So this differential equation is easily integrated if you express it in terms of 1 over GR, because then it becomes a linear partial differential equation. And the final result is GR of mu equals the original coupling GR0 divided by 1 minus 3 over 4 pi squared GR0 times log of mu divided by mu0. Okay. So this is just the result. Okay. But equivalently, we can study the GR of S that I have defined here. Let's look at that. Okay. So now, let's look at this equation. There is a 1 minus a log of mu because the coefficient of the beta function is positive. Okay. So what you see is that when mu goes to 0, when you want to compare the renormalized coupling at a scale mu is not, and the renormalization at a scale mu, which is very small, namely low energy, then the log becomes very negative. So this becomes very positive. So GR of mu goes to 0, and it goes to 0 as, in fact, 1 over log of mu. Okay. So this means that the effective coupling at large distance at low energies goes to 0. The theory interacts less at low energy or large distance than at high energy. So this is often called infrared asymptotic freedom. Okay, and it's related to a phenomenon which is in physics, which is the phenomenon of screening. The interaction between two remember, 5-4 theory describes the hardcore interaction between point-like particles. And what this calculation tells you is that because the particles are surrounded by a virtual cloud of particles and antiparticles, the particles, may, interact with some of those virtual particles, and the net effect is to decrease the interaction. It's the screening phenomenon. Okay. Now, at high energy, of course, that's the opposite. When mu grows, the lob becomes larger, and then you run into a problem, because then you reach the 0 of the denominator. So it means that at a finite energy scale, which you can compute easily, which is mu equal mu0 exponential of 4 pi squared divided by 3 times 1 over GR0, then GR or mu becomes infinite. So there is a maximal energy scale. So at this scale, the theory breaks down. Okay? So of course, this, if you start from a theory where GR0 was very small, and that's what we did in perturbation theory, 1 over GR0 is a large number. The exponential of a large number is a very, very large number. So this is going to be a very, very large energy scale. This scale is very large. This is exponential of 1 over the coupling constant. But still, there is a problem. Okay. You cannot see this problem in perturbation theory because these scales is something that you cannot compute this scale in perturbation theory. It involves exponential of 1 over g. So in some sense, the corresponding length scale is infinitely small in perturbation theory. So it's a non-perturbative phenomenon. And it's a non-perturbative phenomenon because you see, if you take this formula and you expand it in powers over g, you see the pole only if you sum up the infinite series in GR. And this infinite series in GR, the first term, so GR is defined by this plus this equation at leading order. And when you look at which are the diagrams that contains the next order in the expansion of the 1 over minus GR log, in fact, you discover that they come from diagram like this one, and diagram like this one, plus diagram like this one, plus diagram like, I don't know, this one. So they come from a class of high-order diagrams that contains bubbles inside bubbles inside bubbles inside bubbles. Because you see this, if you reduce these bubbles to 1 point, you get this. If you reduce these bubbles to 1 point, you get this. So there is an infinite subclass of what is called leading diagrams, which contribute to this problem. So it's a non-perturbative in the sense you see it only if you are able to sum an infinite class of diagrams. But from this equation, this is what renormalization group theory is doing. Okay. So this is a problem for the phi-4 theory, but we treated it as a toy model to study phi-4 theory. But still, this is a problem for phi-4, but it's also a problem for QED. And it's a problem that was first, I think, discussed by Landau in the 60s, the famous quantum matter and high energy theoretical physicist. So Landau, and this problem is also denoted the problem of Landau ghosts. Well, ghosts for some historical reason. So it's a problem for phi-4 or for QED. But of course, this problem is not there for theory where the beta function has a negative sign. Okay? So it's not a problem for QCD, the theory of strong interaction, and for theory involving non-abelian gauge fields. Because in that case, a famous discovery by calculation by Toft and then by Gross, Politzer, and Wilczek showed that for non-abelian gauge theories, the beta function has a negative sign. And if you have a negative sign, you have a plus sign, so it's the opposite. The effective coupling constant goes to 0 at high energy, and it becomes large at low energy. But then we know that the dynamics of gauge field is something highly non-trivial with non-perturbative phenomenon like confinement and things like that. And for QCDs, it's called asymptotic freedom in the ultraviolet, so at high energy. That's ultraviolet. Okay. And so, finally, there is something else that I wanted to discuss. Oh, yes. And this is, okay, let me just say a single word in 2 minutes about renormalizable versus non-renormalizable. Here it is. Okay. I treated the case of one loop. Okay. We have seen that phi 4 in D equal 4 can be renormalized. And of course, the theory is what happens for n loops, general n. So is it possible to extend this framework? So there is a theory of renormalization theory that was developed in the 50s and the 60s, so more than basically 50 years ago, which is a well-established mathematical theory. And the theorem, there is a theorem which is called BPHZ theorem. Well, B is Bogoliubov, another famous Russian physicist. P is Paratyuk, one name. HEP, H is for HEP, and Z is for Zimmermann. This is Bogoliubov, Paratyuk. I'm sure this is not the correct spelling. HEP and Zimmermann. So, UN because it's German. HEP is a Swiss physicist who turned to biophysics, biology, a long time ago. And Zimmermann, I think he's dead, but he's a German physicist. And this theorem basically states that this is possible for normalization. It's possible at all orders in perturbation theory. It's a very important but technical theorem. It says that you can the kind of game that I played can be played by modifying the coefficient A, B, C so that everything is finite in 4 dimensions. So why is it so? The idea is based on the idea of power coupling. Okay, because in 4 dimensions, we have seen that if you consider the 4-point function at one loop, it contains only log of lambda. Okay? And that's because in this diagram, we had an integral d4k associated to the loop, and a propagator 1 over k squared associated to the lines of the diagram. Okay? And this means that, in fact, there is a logarithmic divergence if the number of loops minus the number of lines is positive. So if this is positive, you have a divergence. If this is 0, there is a logarithmic divergence. And if this is negative, this is convergent. Okay? But here there is a 4. So in fact, there is a d times the number of loops. And there is a factor 2. I'm sorry. No, there is a minus 2. Because each propagator, as I mentioned, 1 over k squared, and each integral over the loop has dimension d. So you see that this number, which is called the degree of divergence of the graph, G, the degree of if you want, of divergence, the graph tells you whether you expect to have ultraviolet divergence in the diagram. Okay? And now, it's an exercise. If you take a general irreducible 4-point function, okay, not only a diagram like this one, but like this one, or something even more complicated than this diagram, for instance, which you can check, is a 3-loop irreducible diagram. Well, you can check that in 4 dimensions, for d equals 4, omega equals 0. So you only get logarithmic divergence. Okay? Of course, for 2-point function like this one, or this one, or some more complicated diagram, then you check that omega equals 2. It's 2 because, for instance, here you have 1 loop, but 1 line. So it's 4 minus 2. So omega equals 2. And so this is an irreducible 2-point diagram. And for higher order, omega is negative. So at all orders in perturbation theory, only the 2-point function contains a log of lambda, and this gives a divergence like lambda squared. Okay. So this means that in d equals 4, basically, you expect that you have to change in the action to introduce counter terms proportional to phi 4 and phi squared term. Well, in fact, the fact that there is log squares means that you may also have divergence like p squared log of lambda. This is allowed. So phi squared and d phi squared counter terms are necessary. So you just have to change the coefficient in the original classical action to make the theory ultraviolet finite. So in this case, the theory is said to be renormalizable. Okay. But now, if the dimension is larger than 4, then it becomes worse, because the more loops you have, the more the diagram is divergent. And if d, for instance, if d is larger than 4, you can check, for instance, that the degrees of convergence of a diagram is the degree of convergence is d equals 4 plus, of course, d minus 4 times the number of loops. So a diagram which was convergent in 4 dimensions, like for instance this diagram, which had degree omega 4 equal minus 2, which is convergence, becomes divergent in d equals 6, because you get minus 2 plus 2 times 1. That's 1 loop. So this means that if d is larger than 4, for instance in d equals 6, you need a phi 6 counter term. And the more you go in perturbation theory, the more divergence you have. So phi 8 counter term will be needed, and phi 8. So you need an infinite number of counter terms. Okay, and you lose control. So in this case, the theory are said to be non-renormalizable. And the framework of mastering the ultraviolet singularities by imperturbation theory fail. Okay, so phi 4 theory is renormalizable in d equals 4. At the non-renormalizable is the dimension of space is more than 4. And this argument of power counting, just defining what is the degree of divergence of a diagram and counting this, of course, can be done for other theories. For instance, in QED, that's the same thing. In QED, you have a different kind of thing, but the 2-point function here between, well, with fermions contains, you can count the degrees of divergence. This what is it? An electron propagator is divergent. The photon propagator, I think, is divergent. And the 2-point function, the 2-point, the vertex of interaction between the photon and the fermions are divergent. I'm right. Yes. And so QED in D equal 4 is renormalizable. But in 6 dimensions or 5 dimensions, it won't be divergent. And these diagrams have degrees of divergence 0, I think, omega equals 0. This is 0, and this one has dimension 1, because it corresponds to a normalization of the mass. Okay, so well, I took more than my time, but so let me end the discussion of normalization in perturbation theory. Okay, thank you. And sorry for it. 2 minutes went to, were renormalized to 10 minutes.